Video here on rational functions. We'll see how far we get here, but I know a lot of students want some help with these. So basically, to start off here, vertical asymptotes in holes, the first one here, you always want to factor the top. So this would be 3 parenthesis x minus 2. You want to factor here because we got to see if anything cancels. On the bottom here, we have x plus 2, x minus 2 when we factor that correctly. So obviously we can see here that the x minus 2's are canceling. So that means right there that there's gonna be a hole at an x value of 2. Because that's what happens. We've been talking about that in class. That's what happens. There's gonna be a hole. Basically like the graph's gonna go, there's gonna be a hole there and it continues. There's no value there, but there's not a vertical asymptote. This one here does not cancel off. So there's a vertical asymptote there, and it's at the line x equals -2. So make sure you have that entire equation there. All right, to find the horizontal or oblique asymptote, we've been using the long division. So the idea is the bottom goes on the outside here. So x squared minus 4 on the outside. And if we put 3x minus 6 on the inside, you'll kind of notice something funky happening. We need to find something that we multiply by x squared to get 3x. That's like powering down. So if you're powering down, the best thing I would say is put a filler out here and it should make sense. So now we think, okay, I need something up here to multiply by x squared to get 0x squared. And the only number is 0. So that means that the horizontal asymptote there is going to be y equals 0. So that happens in that situation. Number 11 here, we cannot factor the top with that plus sign, no GCF. We can factor the bottom, and the bottom goes to x times x plus 3. Just pull out a simple GCF there. So what we have here is nothing canceling, but we do have a vertical asymptote here. So the vertical asymptotes would be at x equals 0, because that's the 0 here, and then x equals -3, but there's no holes on this problem here. Okay, so horizontal oblique, here we go again, put it into long division. I would have 3x cubed on top, and out here, I'm sorry, in the inside, and in here we'd have x squared plus 3x. Now before I wrote the rest of it, I just want you to see here that we can multiply by x squared to get 3x cubed. So what I'm going to do is I'm going to put some fillers in the middle here so that we actually have everything lining up for long division. Now if we were to carry out this long division entirely, this would be kind of a long process, but this isn't going to take as long because literally all we have to do is say, all right, what times x squared gives me 3x cubed? I want to be able to subtract here in a moment and have those cancel. I got to have 3x cubed here. Well, hopefully we can see that that would be 3x. So I'm going to line that up with my like terms right here. So I'm going to put a 3x, and then this time I do have to multiply back. So that I would get the 3x cubed, but also 3x back to the 3x would give me plus 9x squared. So again, that's why we need the filler here, because now, switch colors, we need to subtract. If we subtract here, they cancel. If we subtract right here, we actually get a -9x squared. Okay, so now what times x squared is going to give me -9x squared? Well, that's just going to be a -9. So actually, this is what we call an oblique asymptote. It has a slope of 3 in this case, but that's the oblique asymptote there. All right, I'm going to pause this video here because I want to make sure it records.